All right. Welcome back, everyone, to our third day of the this Simons Collaboration meeting. Just to start with the announcement that unfortunately the second speaker today is unavailable, so we will not have the second speaker speaking today. But we're very pleased that we have our first speaker, Brendle, who's going to tell us about ancient solutions to the Ricci flow in dimension 3.
Thank you very much for the introduction, and thank you for the invitation to speak. In this lecture, I want to discuss some results from the last couple of years, leading to a classification of ancient solutions to the 3D Ricci flow. So I would like to start off and tell you some basic definitions, what an ancient solution is, and why these are objects that we want to study in order to understand singularity formation in geometric flows. So first of all, the definition is very simple. Suppose that we have a solution to some geometric evolution equation, then we say that this is an ancient solution if the solution is defined on an interval that extends all the way to time minus infinity. So I want it to be defined on an interval minus infinity to capital T. Now, it's possible that the solution could be defined infinitely far going into the future, but we don't care. We basically only care about the back history. So as long as we can extend it backward to time minus infinity, then we call it an ancient solution. Right, so the way you should think of this concept is that an ancient solution to a parabolic PDE, this is exactly analogous to an entire solution of an elliptic PDE. Now, when you study elliptic PDEs, linear PDEs, or maybe the minimal surface equation, or another elliptic PDE, then in order to understand singularities, what you often do is you perform a sequence of rescalings near the singularity, and then you pass to the limit. And so then after passing to the limit, then you typically get an entire solution. So that's why entire solutions to elliptic PDEs are important. Now, something very similar happens in the parabolic world. So ancient solutions, they arise as limits of rescalings of geometric flows. And so let me just mention here the basic mechanism in a very simple example. Suppose that we have a solution to the Ricci flow starting from some initial metric on some manifold M, and suppose that the solution goes singular at some finite time, capital T. Then let's consider a sequence of points in space-time where the curvature goes to infinity, and let's choose the sequence in a certain way so that the curvature at xj, tj dominates the curvature at all other points in space and at all earlier times. And yes, so that means if you take the slope of the curvature over all previous times, then that's less than maybe twice the curvature at the point xj, tj. And of course, there's nothing special about the number 2. All I need is that there's some constant. So then under this assumption, I can dilate around xj, tj to make the curvature 1. Okay, I can always do that, of course, but under this assumption, I can pass to a limit, and then the limit will be an ancient solution. And so the basic point here is that prior to rescaling, the solution has a certain finite positive lifespan, and then you perform the dilation, then the lifespan becomes huge. And then as you pass to the limit, then in the limit, you're going to get an ancient solution. So it's the same mechanism like in the elliptic PDE, that in the elliptic setting, it's an entire solution. And here it gives you an ancient solution. Now, in the Ricci flow, typically, you want to throw in an extra condition. And This is based on a famous law by Perlman, which says that any limit of rescalings of the Ricci flow at a singularity must be non-collapsed. Now, the definition of non-collapsing, this is that we want the volume of a geodesic ball of radius r centered at any point p. We want that bounded from below by kappa times r to the n, where n is the dimension, provided that the maximum curvature in this ball is bounded by 1 over r squared. So basically, if you have a ball such that the curvature in that ball is controlled, then assuming that the solution is non-collapsed, you will get a lower bound on the volume. So very loosely speaking, non-collapsing means that curvature controls volume. Now, of course, the key insight by Perlman is that if you have an ancient solution that arises as a blow-up limit at a finite time singularity, then it has to be kappa non-collapsed. So if you have a solution to the Ricci flow starting from some initial data, then the solution will satisfy this non-collapsing condition on any finite time interval, but the constant kappa that could deteriorate as t gets large, but only at a controlled rate. Okay, and so this motivates this definition by Perlman, where he says that a solution MGT is an ancient kappa solution. If first of all it's ancient, then it's assumed to be complete. Then we want it to be non-flat. Then we want it to have bounded and a negative curvature. And finally, we want it to be non-collapsed. Now, the non-collapsing, this is very natural because that needs to be satisfied for any blow-up limit of Ricci flow at a finite time singularity. And then the non-negative curvature, well, you can assume that in any dimension, but it's particularly natural in 3D because by the Hamilton-Ivy estimate, we know that any blow-up limit at a finite point in time has to have non-negative curvature. And then the only condition that's not so obvious why you want to assume that this is boundedness of curvature, but it turns out that you can restrict basically to this class of solutions with bounded curvature. That's not quite as intuitive why you can do that. Okay, so this is basically the natural class of objects that we want to look at. And of course, well, if we go back here, the reason this is a natural class of objects is that these are exactly the properties that we expect to be satisfied on a blow-up limit. And indeed, Perlman proved that in 3D, you can rescale based around any sequence of points with curvature going to infinity, and you will get such an ancient kappa solution. Now, let me tell you about the known examples of ancient solutions. And so let me begin with the simplest case. And let's start with the 2D case. And here, well, one obvious example are the shrinking spheres. So here, the underlying manifold is an S2. The metrics GT have constant curvature for each t. But as time evolves, the metric gets smaller, the radius gets smaller, and the curvature gets bigger. And well, you can write these solutions down explicitly. You get negative 2t times the standard metric. And the negative sign shouldn't confuse you because we're assuming that t is negative. So these collapse to a point, but they're non-collapsed in the sense of Perlman's definition, because even though the volume gets smaller, the curvature also gets larger. So in the sense of Perlman's definition, these are non-collapsed. Then maybe the second example you could look at is S1 cos R, and they wouldn't move at all, and they would be collapsed. Now, a more interesting example is the cigar soliton. And you can write it down explicitly So the underlying manifold is just R2. And then the metric looks like this. You take, so it's conformal to the Euclidean metric, and the conformal factor is 4 over a constant plus norm x squared. And the constant is e to the t. Now you can just plug that into the equation, and it turns out this is a solution. And it's also quite easy to see that is e to the t doesn't really change the geometry. So for different values of t, these metrics, they are isometric to one another. So and the diffeomorphism is basically scaling, a radial scaling by a factor which is given by e to the t over 2, basically. So the point is that these metrics are not identical because the metric is not flat. So the metrics change, but they only change in a kind of trivial way, where the metric at time t is gotten by pulling back the metric at time 0 by a diffeomorphism. And so that's what's called a steady soliton. So it moves in a self-similar fashion, moves by diffeomorphisms. Now, if you look at the asymptotic behavior of this thing near infinity, well, if x is large, the e to the t becomes negligible. And then what you see is the conformal factor of the cylinder. So therefore, this cigar soliton, this is asymptotic to a cylinder of some finite radius as you go out to spatial infinity. And so in particular, it's pretty clear that this has to be collapsed because S1 cross R is collapsed. And you can also see it like this. You can take, because the curvature tends to 0, because an S1 cross R is flat. So then at infinity, the curvature is tiny, and you can compute the rate of decay. But then this means you can test the non-collapsing condition on large balls, and then it will fail. Right. Now, here's a slightly more complicated solution. This is called the Rosenau solution. You can again write it down as a conformal factor, and well, I did so here. So you take the Euclidean metric, and then for any negative time t, you can express the conformal factor basically as the reciprocal of a quartic in x. And now it turns out that even though this is a metric on R2, it actually extends smoothly to a metric on S2 using stereographic projection. So this is not really a metric on R2, but it's a metric on S2. And as t tends to 0, it collapses and becomes round after the scaling. So it looks like these shrinking spheres. But then as you go backwards in time, it looks like a very sort of elongated oval. So it has like a very large cylindrical piece in the middle, and then it has caps on either side. And the caps look like the cigar soliton, and the piece in the middle is basically an S1 crossed with an interval, and the S1 has basically a finite radius, but it does a little bit of positive curvature, so it's a little bit sort of convex, so to speak. Right. Okay, and this thing, like the cigar soliton, this is collapsed. Now, what Perlman proved is that up to scaling, the only ancient kappa solution in 2D is the family of shrinking spheres together with its C2 quotient on RP2. So you basically just get 2 examples, and modulo of quotients, you only get 1. Now here, remember that we're looking at ancient solutions that are non-collapsed. Now, if you allow collapsed solutions, then you can still get a complete classification, and that was done by Pascalopoulos, Hamilton, and Sesson. And the only examples are the cigar and the Rosenau solution. So this list is basically exhaustive up to quotients and scalings, of course, and diffeomorphisms and translations in time, sort of the trivial things you can do. But let me not get into this, and for the purposes of this lecture, let me just focus on the non-collapsed case, since this is what we need to understand singularity formation.
Should I just ask one quick question? Just is there in infinite time behavior, then are you interested in collapsed ancient solutions?
Yes, so in infinite time, you can get different things. So for example, like in Perelman's proof of geometrization, there are these collapsing situations that come up where you get fibered spaces. And in that case, you could get things like you could get tori, for example, or fibered spaces. And these are all collapsed. So this is basically a different world. Even in that case, the collapse case plays some role because basically it has to do with a trade-off between curvature and time. So like it depends on something like the product of curvature with time. So if curvature is times time is large, you're basically still in this machine. So basically understanding the non-collapse case will tell you something about the long time behavior, but it will not tell you everything. All right, so let me continue with the 3D case. And so here again, you have the shrinking spheres. Then you can look at the shrinking cylinders where you just take a 2-sphere crossed with R, and both of these are non-collapsed. So basically taking a Cartesian product with a line will not affect whether a solution is collapsed or not. Now you can take the cigar soliton crossed with a line, then that gives you an ancient solution, but it will be collapsed because the cigar is collapsed. Okay, now the next example, this is the 3D analog of the cigar soliton, and this is a steady soliton which is rotationally symmetric. And well, finding this is quite a subtle problem. You have to understand very carefully a complicated ODE, but this was constructed rigorously by Robert Bryant. And this soliton, so in a way, it's the analog of the cigar, but this analogy also has its limitations because while the cigar opens up like a cylinder, so the radius of the cross-sectional circles on the cigar has a finite limit. This one, the Bryant soliton 3D, this opens up like a paraboloid. So if you go out to distance R, or the distance S, then the cross-sectional S2 has radius which is on the order of the square root of S. So the asymptotic behavior is totally different, which has to do with the fact that S2 has positive curvature, while S1 does not. And so this solution, unlike its 2D counterpart, is actually non-collapsed because basically there's enough volume so that, like, if you look at the appropriate ball, then it has enough volume and the ball cannot get too large because of the curvature condition. Now there's another ancient solution, which is the 3D analog of the Rosenau solution. And this one is compact, like the 2D Rosenau solution. It's diffeomorphic to S3. And it has a very similar behavior as the Rosenau solution. So as you go forward in time, it collapses to a point and becomes round after the scaling. So it looks like the shrinking spheres as you go forward in time. And as you go backward in time, it looks like two Bryant solitons joined together. So you have these two curves that each look like a Bryant soliton. And then in between, you have basically a cylindrical piece. But the radius of the cylinder will be very large depending on time. And so this is non-collapsed, and maybe that's not too surprising because an S2 crosed with an interval is non-collapsed, and so is the Bryant soliton. And the ancient solution found by Perelman is basically made up of, you can sort of think of it as being made up of these pieces. I should say that it's rotationally symmetric. So both the Bryant soliton and Perelman's ancient solution are rotationally symmetric.
So Zeeman, can I just ask, how did Perelman find this ancient solution? Was it by that kind of gluing type construction, or was it by sort of rotational symmetry and arguing with some ODE thing, or what was the?
So he found it by a limiting argument. Basically, he looked at a family of initial data, and then he evolved them, and he showed it the sort of a critical value for which you form a singularity that has to look. So yeah, so let me make it more precise. So you have the, basically you start with oval type shapes, and then you evolve these, and you try to take a limit of these, and then in the limit you get this ancient solution. But you start from sort of more and more degenerate initial data, and then they will exist for, the solutions will exist for longer and longer times. So it works a little bit similar, in a somewhat similar fashion, like these arguments in mean curvature flow, for example, in Tsuchiya Wang's paper, where he constructs the what's called the flying wind soliton, and that's done by a limiting argument. And Perelman's construction is basically in that spirit.
Thank you.
Thank you. Okay, let me tell you what's known about these ancient kappa solutions. So first of all, as I mentioned before, they, like any singularity in 3D Ricci-flat that occurs in finite time, is modeled on one of these. So all the high curvature regions look like an ancient solution. So that motivates basically why we look at them. And then Perelman proved this structure film, where he sort of qualitatively described what they look like. And there are two versions of this result. There's a version in the non-compact case, and this is the one that's used in the proof of the Poincare conjecture. And then there's a companion film in the compact case, which I will describe next. So let me begin with the non-compact case. So if you have a 3D ancient solution, which is non-compact and kappa non-collapsed and satisfies the other conditions, then it's either locally isometric to a family of shrinking cylinders. So in other words, it's up to isometry. It's just a quotient of these shrinking cylinders. Or the other possibility is that the solution is diffeomorphic to R3, so you understand its topology. And moreover, you can understand its metric structure. Namely, what happens is it has the structure of an infinitely long epsilon tube. So it's sort of half infinite, infinite to one side. And then on the other side, there's a cap attached. Now, I should say what I mean by an epsilon tube. So an epsilon tube, this is a region that's gotten by gluing epsilon x. And an epsilon x, that's a region that after the scaling is epsilon close in the C1 over epsilon norm to a piece of a cylinder. So that's basically like a piece of a metric cylinder up to an epsilon perturbation and up to scaling. And so you have basically this tube, and you understand extremely well how it looks like in a topology that's as good as you want. And then this tube is capped off by a cap, and the cap is basically understood to be the exceptional set of all points that don't lie on an epsilon neck. And so basically, the smaller you choose epsilon, the larger this exceptional set becomes, and the larger this cap becomes. But it still has controlled geometry. So you can control its maximum curvature by its minimum curvature. You can control the diameter by the maximum or minimum curvature. So basically up to a single scaling factor, you control this cap in any topology you want. Now, there's a companion result in the compact case, and in that case, the result is that either you get a family of shrinking spheres or a quotient of that. So let's assume the solution is simply connected, that will get rid of the quotients. Then it's either a family of shrinking round spheres, or else the thing is diffeomorphic to S3. And when T is very negative, it has the structure of a finite but very long epsilon tube with caps attached on each side. And again, these caps have controlled geometry up to scaling. And of course, the prototypes that you should think of are the Bryant-Soliton and the Hellman solution. And they have exactly this structure, that you have a tube with a cap attached in the non-compact case and a tube with two caps attached in the compact case. Okay, so this is the sort of the qualitative picture. And I should say that this qualitative picture, this is entirely sufficient for topological conclusions. So this allows you to do surgery, and then basically in the surgery, you cut off these caps, but then you know what the geometry of the caps is, and that's what allows you to recover the topology in the end. But one point to keep in mind is that in Perlman's work, it doesn't really matter what this cap looks like, as long as A, you understand its topology, and B, it's attached to a neck on which you can do surgery. Okay, now in Perlman's paper, he conjectured that actually there should be very few examples of ancient solutions. And specifically, he conjectured that in the non-compact case, apart from the shrinking cylinders, the Bryant-Soliton should be the only example. And so this is a conjecture I proved back in 2018. So up to scaling and pullback by diffeomorphisms, every non-compact ancient kappa solution in 3D must be either the family of shrinking cylinders or quotient of that, or else it has to be the Bryant-Soliton. Now again, there's a companion result in the compact case, and in the compact case you can conclude that up to scaling and translation in time and diffeomorphisms, the only examples are the shrinking spheres and the quotients, and the Hellman solution. And then this one also has a C2 quotient, and these are the only examples. Right, now in this lecture, I want to focus on the non-compact case. So basically, the non-compact case is a necessary step towards understanding the compact case. So you have no chance to understand the compact case if you don't first understand the non-compact case. And the reason is basically that if you take a sequence of rescalings of a non-compact solution, you always get a non-compact solution. But if you take a sequence of rescalings of a compact solution, you could either get a compact or a non-compact solution. So the compact case can sort of degenerate into the non-compact case. Right, now let's focus on the non-compact case. And this result has basically two parts, which I call theorem A and theorem B. And from A, that's a result entirely about rotationally symmetric solutions. So it says that if you have a non-compact ancient kappa solution in dimension 3, which has positive sectional curvature and which is rotationally symmetric, then it has to be isometric to the Bryant-Soliton up to scaling. So basically, this is just saying that no counterexample to Perlman's solution can be rotationally symmetric. Of course, the advantage here is that you can make use of all the simplifications that come with the assumption of rotational symmetry. You can reduce it to a scalar equation in one space and one time variable. And in particular, a crucial point is that this allows you to use barrier arguments, which for Ricci flow in general, you can do, or at least we don't know how to do. But in the rotationally symmetric case, that's possible to do. And for example, that goes back to, I mean, that's been used in works of Angerman and Knopf and other authors. So yeah, and of course, a lot of other things simplify as well. So first of all, you have to basically nail down the rotationally symmetric case, but at least there's a much larger toolbox that you can use. Okay, so I will not go into the details of theorem A, and instead I want to focus on theorem B, which is the statement that every non-compact ancient kappa solution in dimension 3 with positive sectional curvature is rotationally symmetric. Now, the assumption of positive sectional curvature, that's no big deal because we're assuming the negative sectional curvature anyway, and then by like the strong maximum principle, you either get strictly positive curvature or else you're on a cylinder. And in the latter case, we're done anyway. So we want to focus on the case of positive sectional curvature. And then the goal is to prove that such a solution has to be rotationally symmetric. Now, one kind of unusual and in my view remarkable thing is that the proof of theorem B uses theorem A in a crucial way. So in order to prove that every solution is rotationally symmetric, you need to know what the rotationally symmetric solutions are. And this sounds a bit counterintuitive because, I mean, if you have a solution that's not rotationally symmetric, why does it help that we could classify it if we knew it were rotationally symmetric? So it looks like it's as far as the proof of rotational symmetry is concerned, it seems like a useless piece of information that you know what the rotationally symmetric examples are, because we're trying to prove it is rotationally symmetric. But it turns out the reason why it's useful is because if you have a non-rotationally symmetric solution, there are certain limits of rescalings that will give you rotationally symmetric solutions. And then theorem A comes in handy because it will tell you what these particular limit solutions look like. So yeah, so you have to do it in a particular order. You have to do theorem A first. Okay, now let me talk about the proof of rotational symmetry. I mean, yes, so I've already hinted at the classification of rotationally symmetric solutions will play a role, but as a warm-up, let me talk about the classification of steady solitons. So this is a result I proved much earlier in 2012. And in a way, it's quite a bit simpler, but some of the main ideas are the same. And so it helps illustrate the idea. And there's a second reason in that a classification of solitons, this is needed to prove the general case. So basically, to prove the general case, I need to A, know the classification of solitons, and B, I need to know the classification of rotationally symmetric ancient solutions. So let's turn to solitons. So a steady gradient Ricci-soliton, this is characterized by the condition that the Ricci tensor is the Hessian of a scalar function, and then it moves by diffeomorphisms, and the diffeomorphisms are generated by the gradient of f. And such a thing is a special case of an ancient solution. And then it turns out that, well, it's a special case of Perlman's conjecture, that if you have a steady gradient Ricci soliton, which is non-collapsed and has positive sectional curvature, then it has to be the Brine soliton. And right, so the idea of the proof is that by Perlman's work, we know that outside of some compact set, the solution looks like an epsilon tube. So every point lies on an epsilon neck, and basically the epsilon gets better as you go farther and farther out to infinity, because if you have a smaller epsilon, then this result of Perlman is still true. It's just that the exceptional set of points that don't lie on an epsilon neck is larger, but it's still a bounded set. So basically, as you go out to infinity, the end becomes more and more neck-like. Now, in the soliton case, it's also not terribly hard to show that this manifold has to open up like a paraboloid at infinity. So basically, you have this thing where at infinity, it looks like a paraboloid, and it becomes quite symmetric. I mean, up to errors of order epsilon as you go out, but you don't really know what's happening in the inside in any compact set. Now, the way you get around it is, well, you can construct approximate killing vector fields U1, U2, U3 near infinity, because basically at infinity, you have sort of an approximate SO3 action. You don't have an exact action because this thing is not exactly symmetric at infinity, but it becomes symmetric to a better and better approximation. And that gives you these approximate killing vector fields. And then what you do is you solve a linear elliptic PDE with these approximate killing vector fields as the boundary condition at infinity. So you construct solutions of this PDE that are asymptotic to U1, U2, U3 at infinity. And then, well, then let's call the solutions V1, V2, V3. And then the crucial part of the argument is that you apply a maximum principle. You use the maximum principle, and it turns out that the Lie derivative of the metric along these V1, V2, V3, this satisfies a PDE. And you can apply a maximum principle to that PDE. And then you can show that because the Lie derivatives are small at infinity, they have to vanish identically. And that gives you exact killing vector fields. And then you're done. And then it's rotationally symmetric. And then in that class, the uniqueness follows from Robert's work. Okay, so after this digression, let's go back to the general case. So let's assume we have a non-compact ancient kappa solution. And let's assume it has a positive sectional curvature. And just to fix notation, let me denote by R max the sup of the scalar curvature at time t. So I don't know if R max is attained at this stage. So it could be just a supremum rather than a maximum. Now, the first step in the proof is to invoke a result by Yong-Jia Zhang, who proved that any ancient solution that doesn't split as a product is of type 2. So if it's not a cylinder, then it has to be of type 2, meaning that the lim sup of T times R max of T will be infinite. And okay, so that uses basically things from Perlman's work as well as the next stability form of Kleiner and Roth. And so in the mean curvature flow case, that statement is very easy to prove. In the Ricci-flat case, it's more delicate, but it's nevertheless you can do that, and that is done by Yong-Jia Zhang. And then there's an old principle by Hamilton that if you have a type 2 ancient solution, then you can do a point picking and in space-time to produce what's called a type 2 blow-up limit. So you can find a sequence of points p hat k and a sequence of times t hat k going to negative infinity, such that if you rescale around that particular sequence of points in space-time, then you get a steady gradient Ricci-soliton. And that's that's quite a non-trivial argument because it uses the Harnack inequality, which is a deep result. But basically, this result has been known since the 90s, that if you have this type 2 behavior, then you can produce a limit where the scalar curvature attains its space-time maximum, and then the Harnack, basically the rigidity statement in the Harnack inequality will tell you that it has to be a steady soliton. And then, well, by the classification of solitons from the previous slide, we know that it has to be the Bryant soliton. So the upshot is that there exists some sequence of times t hat k going to minus infinity, such that at these times the cap looks like a piece of the Bryant soliton. And when I say looks like, what I mean is it converges in the Cheever-Gromov sense to a piece of the Bryant soliton up to rescaling. Okay, now of course, so what we know at this stage is, so at every point in time, this thing looks like a cap with a tube attached, a cap attached to a tube. That's true at every time. And then there are these special times that come from basically this type 2 asymptotic. And at those particular times, you know exactly what a cap looks like, and it has to look like a piece of the Bryant soliton. So for all times, you know something, and for some times, you know a lot more. But the problem is these times could be like far apart, and we don't really know what happens in between. So in between, the cap could get deformed, and it could look totally different. Okay. Now, what we really want to do is that we want to make an argument that the symmetry is preserved in between these times. Now, when I say symmetry, what I really mean is approximate symmetry. And basically, if you go back to the previous slide, at these times t hat k, the solution is approximately symmetric because the cap is approximately symmetric because it looks like the Bryant soliton, and away from the cap with a tube, which is also approximately symmetric. So basically you have this approximate SO3 action, but you only have it at this particular point in time. And so then what you need is some kind of argument that tells you that approximate symmetry is preserved. Okay, let me explain the basic idea behind that. So let's suppose we have a solution to the Ricci-flat. Let's suppose we have a time-dependent family of vector fields, which evolves by this particular PDE. So DDTV is Laplace V plus Ricci V. Now, the right-hand side, the Laplace V plus Ricci V term, this is the same operator that came up in Hans-Joachim Heinz's talk the other day. And basically, this is sort of the linearized version of the harmonic map equation. And here, we are looking at the parabolic version of that, and it's the linearized version of the harmonic map heat flow, basically linearized around the identity. Okay, so let's assume we have a family of vector fields that evolve in this way. Then let's denote by h of t the deformation tensor, the Lie derivative of the metric. And then one crucial observation is that this h satisfies a parabolic PDE. So the h by dt, this is the Lichnerowicz Laplacian of h. And well, I can write that out for you. So Laplace sub L of h, this is the Laplacian plus these lower order terms. Now, everybody who has ever looked at Ricci-flat and has looked at Hamilton's 1982 paper will recognize this equation, because this is exactly the evolution equation for the Ricci tensor that comes up in Hamilton's 82 paper. And so the argument the point of view I would take is that V satisfies linearized harmonic Marquis flow, and H satisfies linearized Ricci-flat flow. And yeah, so in a way, linearized Ricci flow up to this sort of gauge fixing. Right. Now, an interesting point is that, and this is used in many places in the argument, is that this term on the right-hand side in the evolution of V, this Laplace V plus Ricci V, you can express it in terms of H. So this vanishes on a killing vector field. So if V happens to be killing, then dV dt is 0 and H remains 0 and V doesn't change and it remains a killing vector field. And so, of course, then what we want to do is we want to say we have an approximate killing vector field, then we evolve the vector field in this way, and then H evolves by this parabolic PDE, and we want to somehow estimate H. Okay, now the first idea that comes to mind is to use the maximum principle, and you can do some things with that, and that's very important. But it turns out that in some regimes, in some regions, you can do a lot better than that. And so what I want to do is I want to analyze this parabolic Lichnerowicz equation on a background which is given by a family of shrinking cylinders. The idea being that every ancient solution looks like a neck outside a large compact set. Okay, so let's say we're on an exact neck. Then the background metric is given by G bar, this thing, where you have a cross-sectional S2, which shrinks at a certain rate as a function of time. And then there's this DC tensor DC term, which gives you the metric in axial direction. Now, let's suppose H of t is a solution of this parabolic Lichnerowicz equation on this background with background metric G bar, so on a neck. And let's say this H of t has norm less than 1 in the relevant region. And then there's this technical assumption that at later points in time, I need some control over H, but it doesn't have to be as precise. So I can put L to the 10 here. So basically, well, I forgot to say this, I look at a parabolic cylinder, basically where you go backwards in time to distance L, and you go out in space to distance L also. So it's sort of it's much wider in space sort of than in time. And then basically I want this H to be bounded by 1 at time negative L over 2, let's say, and at later times I want some bound, but L to the 10 is enough. Okay, then I want to understand what happens later in time as this solution has had a while to evolve. And it turns out that up to errors that are bounded by constant over root L, so up to very small errors, this H of t will look like basically a superposition of special modes. And the first two terms, they represent rotationally symmetric terms. So basically a rotationally symmetric function times the metric on S2 and a rotationally symmetric function times dc squared. And then there's this strange term here, which is an extra term that comes from the first spherical harmonics. So basically, what this is really saying is that if you have a solution of linearized Ricci flow and you give it some time to evolve, then after some time, certain modes will dominate. And you can basically decompose it into a term that's rotationally symmetric, plus this term involving the first spherical harmonics, plus errors that are capital O of L to the negative 1/2. So to a very good approximation, it looks like this. Now, the proof of this thing, this is completely elementary, because we work on an exact cylinder as a background, then you can do separation of variables. And basically this PDE decouples into a bunch of 1D heat equations after you do separation of variables in spherical harmonics. And then, well, you just analyze the modes. And in the end, you put them together. And that's what you get. Right. Now, this is already an indication that basically the flow should converge, should improve rotational symmetry, because basically if you look at the perturbation of a cylinder, this H describes the perturbation. And then this is really telling you that after you let this evolve, it will look like something rotationally symmetric, plus this psi term, which basically corresponds to a conformal, like to a deformation of S2 under its conformal group, and then a small error. Okay, now let's make this symmetry improvement principle more precise. So now instead of working on an exact cylindrical background, let's work on a neck. So let's say we're in dimension 3, then an epsilon-0 neck. Here's the definition. That would be a region, a parabolic cylinder that after suitable rescaling is epsilon-0 close in DC 1 over epsilon-0 norm to a family of shrinking cylinders. And let's also recall this basic fact from Hamilton's work that any such neck can be foliated by CNC spheres. So you have a kind of canonical foliation, but the foliation depends on time. Okay, now once you're on such a neck, I want to introduce a notion of epsilon symmetry. So there are these two parameters here, epsilon-0 and epsilon-0, this is the neck parameter that tells you how close you are to a cylinder. And then I look at a smaller parameter, epsilon, that tells me how close I am to a rotationally symmetric object. Now, the exact definition involves a couple of conditions, but basically what you want is you want an approximate SO3 action. And I want 3 time-dependent vector fields such that their Lie derivatives are less than epsilon. And of course, you have to, so I want to also control derivatives. I want to control up to 2 derivatives, but that's not terribly important. And then the derivatives have a certain scaling. So I have to scale by the radius of the neck. But morally speaking, what I'm really trying to say is that I want approximate killing vector fields which preserve the metric up to errors of order epsilon. And then basically, the second condition, this is meant to distinguish sort of on the exact cylinder, the rotation vector fields from the translation. So basically, I want these vector fields to be tangential to the CNC foliation. So I want, And then the third condition, this is basically a non-degeneracy condition, that I want these vector fields to be orthonormal, basically when restricted to one of these CNC spheres. This is just to prevent the vector fields from being trivial. Okay, so this is kind of a complicated definition, but the rationale behind it is not that subtle. Okay, now here's the first crucial step in the argument, and this is what I call the neck improvement form. And essentially this says that the symmetry of a neck improves as the neck evolves. Now here's the exact statement. So I can find a uniform constant L and a uniform constant epsilon1. So L will be large, epsilon1 will be small, such that the following holds. So suppose that x0 t0 lies at the center of an evolving epsilon1 neck. And let's suppose that every point in a parabolic neighborhood of size L is epsilon symmetric, then the point at the center is epsilon over 2 symmetric. And of course, the parabolic neighborhood, the size has to be scaled in terms of R, where R is like the radius of the neck up to a factor. So basically, if you have a large neighborhood and every point in that neighborhood is epsilon symmetric, then the center point is epsilon symmetric. Now, the crucial point here is that L and epsilon 1 are independent of epsilon. And this is what allows you to iterate this. So then if you have a bigger neighborhood where every point is epsilon symmetric, well, then you can do this twice and you get epsilon over 4. And if you have an even bigger neighborhood, you get epsilon over 8. And well, it improves very rapidly if you have a sort of a large region on which you can play this game. Now, how do you prove such a thing? Well, the proof takes a lot of technical steps, but basically the strategy is you choose L large, and L depends basically on this mode improvement. So like if you go back to the analysis of this thing, basically you choose the L large to kill this constant, so that the C times L to the negative a half is small. And then having chosen L, you choose epsilon 1 small, so that basically all these approximations are justified because your neck is sufficiently close to a true cylinder. And then you apply this result. So what you really do is you use your assumption of epsilon symmetry in this parabolic cylinder. From there you can get approximate vector fields, then you evolve them by this PDE, and then you argue that the Lie derivative of the metric gets better. And that's done basically by this gadget. All right, so now let me get back into the proof of B. So we have established a bunch of things before. And now let's do the full proof. So the idea is we want to choose the sequence of times tk going to negative infinity, well, the flow looks symmetric, and actually it looks symmetric on a large time interval. And then what you do is you choose a sequence of points epsilon k, a sequence of numbers epsilon k going to 0, such that epsilon k is much bigger than epsilon k hat. Epsilon k hat tells you how symmetric the solution is at time tk hat. And then what you do is you start from time tk hat, and then you go forward in time until, for the first time, the flow fails to be epsilon k symmetric. So initially at time tk hat, it is epsilon k hat symmetric, and then you go forward until you lose epsilon k symmetry. And so then basically there are two cases. Either you never lose the symmetry, and then, well, you can send k to infinity and you get exact symmetry, or the other possibility is you lose this symmetry at some time tk, and tk goes to negative infinity. So this is basically the only thing that can happen if you're not already on a rotationally symmetric solution. And so then you put yourself at that particular sequence and you rescale and take the limit. Now in the limit, you get an ancient kappa solution with positive sectional curvature. And then because prior to rescaling, the solution was epsilon k symmetric, this means that the limit flow is exactly rotationally symmetric. And then from A tells you that the limit flow has to be the Brendle. And so then you're basically at this sort of borderline situation where the flow is still epsilon k symmetric. So it's almost the Brendle because it's almost symmetric, but it's about to lose epsilon k symmetry. Now, what you do is at that time, because you're close to the Brendle, you can understand, you can prove that the symmetry improves. And the way this works is using the neck improvement, you can show that the symmetry improves in the tube region. And then because you know that the cap looks like the Brendle, you can use a different argument to show that the symmetry in the cap region improves. So basically, because you're close to the Brendle, you can show that the symmetry improves in both in the tube and in the cap region. So I told you the basic principle that allows you how to do it in the tube region. The cap region is a bit, this requires another argument based on the maximum principle, which I don't have time to show you, but you can do it because you know you're close to the brine soliton. And so then what it allows you to do is, it allows you to show that at time tk, the flow is not just epsilon k symmetric, but it's an improvement to epsilon k over 2. So it's epsilon k over 2 symmetric. But then this contradicts the definition because of tk, because tk is the last point in time where it's still epsilon k symmetric. So it's basically a kind of continuity argument. You start at this time way back where symmetry holds, and then you go forward until you lose this epsilon k symmetry. When that happens, the solution looks almost like the brine soliton. And when it does look like the brine soliton, you try to show that the symmetry improves, and then it holds a little longer, and that contradicts the maximality of tk. Yeah, so to conclude, this is how you prove zone B, and then if you put it together with the classification of rotationally symmetric solutions, then that gives you the full proof of the conjecture. And then in the compact case, a similar argument gives you rotational symmetry, but then the classification of compact rotationally symmetric solutions. This is a joint work with Toti Deskalopoulos and Natasha Sesson, which requires a lot of extra arguments. Yeah, so I'm out of time, so I will stop here. Thank you.
Thank you very much, Zeeman. Let's show our appreciation for Zeeman's very nice talk. Are there questions or comments?
But does the proof of these conjectures lead to a simplification of the proof of the Poincaré conjecture? Or, I mean,
yes, so what these conjectures tell you is that in 3D Ricci flow, if you have any point where the curvature is large, then it has to have a canonical neighborhood that looks like basically the brine soliton or the cylinder or a sphere. And then, yeah, I guess coming out of the singularity, you can get this thing, this Perlman ancient solution. So it gives you a very quantitatively precise information. But for topological conclusions, you don't need it because in the surgery, you do this. I mean, you do the surgery on the neck part, and the cap you throw away, and then all you need to know to prove the Poincaré conjecture is that the cap has the topology of a disk. So this qualitative picture is sufficient for that. But basically, this thing gives you like sharp. For example, it gives you sharp constants in all these estimates by Perlman because the optimal constants are those on these models, and it tells you basically exactly what you converge to if you rescale around a sequence of points with curvature going to infinity. So it's a quantitative information that needed for topology.
thank you.
Alec?
Yeah, I was wondering, what are the prospects for further applications of the symmetry improvement philosophy?
Oh,
It's been used, it's been applied in different situations, different flows. So I was wondering what the further applications could be.
So I think there's a very general principle behind this. I mean, for example, you can do it in higher dimensions in Ricci flow, you can do it in mean curvature flow, you can do it in various fully nonlinear flows. And I think, I mean, you can basically do it whenever you can linearize. So what makes this valid is basically that in this neck region, you know that you are quite close to a cylinder. And then this evolution equation for the Lie derivative that I showed on a previous slide, that gives you sort of an exact, pull it up again, here we have it. That gives you an exact PDE, which is valid at a nonlinear level. But then you can analyze this operator like on your manifold using the fact that you know that the background is a perturbation like of a model space. And I think that principle should be applicable in many cases.
So it seems like it'll certainly use the assumption of non-collapsing very strongly, because at least we would expect there to be non-rotationally symmetric ancient solutions dropping the non-collapsing condition. At least I know in mean curvature flow, there do exist compact convex ancient solutions which are not rotationally symmetric,
That is
which are collapsed.
Well, basically, yes. So you could have these what are called flying ring solitons, and basically the point is, without non-collapsing, you don't know that every point outside a compact set lies on a net, and essentially, this type of argument gives you more precise information. So it can, I mean, once you know that you're on a net, that means you're quite close to a cylinder, and then you can sort of do a kind of, you can linearize. But the problem is that you also have to localize the argument, since you have some sort of what Kalman would call canonical neighborhoods, and then that you have different models around different points. But I think the general philosophy is that you would want to linearize around each canonical model that you see. So in the collapse case, that type of reasoning might still be applicable in some form, but you would have different canonical neighborhoods that you would have to allow. And I think in other flows, I mean, you could potentially have situations where you want to linearize around more complicated models.
I see. So theoretically, if you want to prove rotational symmetry of something else, like say, I mean, it's an open problem whether the genus 1 shrinkers are rotationally symmetric. So you could consider linearizing around an ongonate torus and do a similar procedure with this, right?
Yes, you could. I mean, I think what is definitely true is that understanding the linearized equation will be important. I mean, one thing here is that separates this problem from the one you mentioned is that here, the symmetry sort of falls onto the solution from infinity, from spatial infinity, and from sort of time minus infinity. Whereas, so that this would be harder to implement in the in the compact case.
Okay, interesting.
Ronan?
Hi, I had a question. Is there higher dimensional versions of the Rosino soliton that you mentioned?
Yes, so the Rosino solution exists in all dimensions. So in 2D, it's collapsed. In 3D, there's this analog by Perelman, which is non-collapsed. And the 3D case is not substantially different from higher dimensions. You can construct it in any dimension, greater or equal to 3.
And is it Kappa non-collapsed in higher dimensions as well?
That's correct. It's only collapsed in 2D.
Okay, thanks.
So are there in once you pass above dimension 3, then are there new sorts of ancient solutions that one should really start worrying about?
Oh, that's a very interesting question. So, I mean, there should be a lot more ancient solutions. I mean, various ancient solutions have been constructed. I mean, for example, there's one that I constructed with the Nikos Kapouleas and I constructed a while back, which degenerates to Eguchi-Hansen methods. And there are probably many, many examples, unless you impose some restrictions. Now, what you can do, if you want to sort of mimic the 3D cases, you can assume a pick condition. And that if you work in that framework, then you can prove results in any dimension that mirror those in 3D. But you would need a curvature restriction that basically restricts singularities to neck pinches. And we have such a condition in higher dimensions. But if you drop that condition, then I would expect you get like a huge zoo of examples.
Mhm. Because there are other things sort of analogous to Bryant solitons in 4 dimensions that were constructed by Appleton, and
Correct.
and you do expect that those appear as finite time singularities.
Well, okay, I mean, this is hard to say, but for now, I mean, one of the few obstructions we have in higher dimensions is not collapsing. So as long as it's not collapsed, it's quite hard to come up with any reason why it shouldn't arise as a lower limit.
And the Appleton ones are non-collapsed. Is that
I believe so. So I would guess that
they somehow look asymptotic to a quotient of Bryant, or
correct.
Okay, well, if there are no further questions, let's thank Zeman again for his very nice presentation.